Welcome to today's webinar with the title, How does your PCB layout influence the costs in PCB manufacturing? The speaker of today's webinar is Mr. Jürgen Wolf. He's Product Manager for Embedding Technology. And now, I wish you a lot of fun and new information.
Thank you, Andreas, for this kind introduction. And I just want to start today and give you an overview of our topics for the next, hopefully, probably 40 to 50 minutes. Depends on how fast we will be through. So what will you see and learn today? I want to talk about PCB arrays and what it means in regard to cost of the PCB. Then we will have a look onto materials and copper prices. Move on to the stack-up of PCBs, so what can be done here to avoid cost. We then go on with mechanical processing, which means we look on drilling processes and routing processes. Move on to the advanced technologies. Advanced technologies means I have some few slides about rigid flex, HDI, and other technologies which can be used in PCBs. In the end, I do have some tips, tricks for layout, what gives us issues during, for example, design rule checking, which still is cost, which is being aroused and therefore needs to be avoided. And in the end, we have a short summary of all these topics on one slide. Okay, so let's start with PCB arrays. But before we talk about the arrays itself, I want to give you a few background information. The question always is, how many PCBs can be placed on a manufacturing panel? And to know what a manufacturing panel is, you have to look on the size of the manufacturing panels which are used in PCB manufacturing shops. And as background information for you, basically all of the PCB materials out there globally are manufactured on big, large panels. There are basically 4 to 5 different formats which are being used by all base material manufacturers. And 90% of the EU and US manufacturers, doesn't matter if they produce in EU or US or if they produce in Taiwan or China, they use the either US format or the uni format. You see the sizes of these formats. Why is this important? This is important because out of these formats, 95% of the PCB manufacturers in the US and Europe use different panel formats because they are being cut out of these US or uni formats, of these big, large panels. This starts with the 1/8 US format, which is being used often for prototypes. We use this in our prototype plant as well. It's 460 by 305. So the big US format is divided in 8 parts, and this is why we have this size. Then there is the 1/4 US format, which is twice the size of the prototype format. We use this as our standard manufacturing format in our series production. And then we have the 1/4 uni format. We call it internally the jumbo format because it's a little bit bigger than the standard format. And so you see, these are basically not only for us, but for most of the PCB manufacturers in US and Europe, the manufacturing panel sizes with which they work in their shops. So what else do you need to know? Each manufacturer needs a border which surrounds the panel. This border is being used for registration and labeling. This can be 10 millimeter up to 20 millimeter. For us, it's mostly 17 millimeters. You will get these numbers when you ask to your board shop, when you ask, for example, our sales colleagues and so on. What does it mean for you? You have an active area which can be used, and this active area can differ from manufacturer to manufacturer. Why do you need to know this active area? Because it depends on how many of your PCBs can be placed in this active area. And I present a sample here for you. On the left side, you see a PCB which outline is being routed. And on the right side, you see the same size of PCB, but here in that case, its outline is being V-scored. V-scored means you make cuts from top and bottom and can break those cuts so that those PCBs almost have no distance in between them when we place them on the manufacturing panel. In this very simple example, you see that already here we can place 33% more circuit boards on a production panel. And since in PCB manufacturing, there are a lot of parallel working steps, for example, when you go to the plating process doesn't differ if there are 3 or 4 PCBs on a manufacturing panel. It always takes the same time in the plating bath. And therefore, the cost for this process is being divided by 4 on the right side, and this being divided by 3 on the left side. So the costs go down for the V-scoring build-up. What is interesting is that this effect is getting greater, bigger, the smaller the PCB gets. Here in that case, it's a real application where we compared for the prototype panel the routing versus the V-scoring. And as you see on the numbers, for the routing, we could only place 56 PCBs on a manufacturing panel, whereas for the V-scoring, we could place 85 PCBs. Yes, we know that often there is an issue with V-scoring when it comes to complex layouts, when there are curves or cuts in the outline and you do not have a rectangular outline. Then often V-scoring is not possible, but maybe you can find a way to combine both processes. Maybe on 2 edges, you could use V-scoring, and on the other edges for curves, roundings or whatever, we only would use the routing process, so that still space could be saved in the active area when the PCBs are being placed. So if you want to know what the best placing would be, just contact us. We can advise you how this can be done. We know as well that often you will not be sent out with single PCBs. Most of our PCBs are being sent out in arrays for assembly purposes, for testing purposes, and so on. And in an array, you always have an edge, and you place the PCBs in this array. And here again, a very simple example, but it shows effectively what might happen in our preparation phase. When we look onto the PCB size, here in this example, it's still the same PCB size, but on the left side, the PCB itself in the array is being routed, and on the right side, the PCB is being V-scored. And here in that case, it doesn't matter if the outline of the array is being routed or V-scored. You still see that due to the size reduction for the V-scoring, we could place 2 PCB arrays on the production panel, whereas for the routing of the PCBs, we only could place 1 PCB on the production panel. So in that case, it's a very extreme example, but we could place 100% more circuit boards on a production panel. And depending on the size of the PCB array, this really happens often. Maybe not with 1 versus 2, but 4 versus 6 or 6 versus 8. This happens quite a lot. And often it's just a few millimeters which prevent us from placing more PCBs on a production panel. So it's always good to know what is the active area, how big should the production, the arrays be, so that we can place most or occupy most of the space on the production panel. To give you some numbers, I did a calculation. I used a 6-layer multi-layer without any rigid flex or HDI built-up, a base material TG150 halogen-free. I used the PCB size 2 by 4 centimeters, an array of 21 by 14 centimeters, 100 micron line space as technology, 500 drills. And yes, I know this is quite a lot, but it's just for comparison reason of different delivery arrays. I used 0.2 millimeter smallest drill size as a calculation base and nickel gold as a solder surface. This is the example for a V-scored PCB array where the PCBs themselves have been V-scored as well. If you do this build up, we can place 216 PCBs on our production panel, on our standard production panel. And if you order 1,000 PCBs from us, this would mean we have to manufacture 5 production panels. If we change the outline of the PCB in the array from V-scoring to routing, we have a distance in between the PCBs. In that case, it would be 5 millimeter distance. And you see that the number of PCBs on a production panel decreases quite a lot. So we only have 160 versus 216 PCBs on the panel. The number of production panels needs to rise, therefore, and therefore the price itself just rises by 17% due to this difference in occupation on the production panel. And for sure, what happens if we increase the distance between the PCBs a little bit more? So we go from 5 millimeter to 10 millimeter space in between the PCBs. We have less PCBs on a production panel, 128 only for that case, and the price rises by 31%. So you still get the same amount of PCBs. It's still 1,000 PCBs. But even between both build-ups or both occupations, the routing with 5 millimeter and the routing with 10 millimeter, the difference is 14%. The PCB itself looks the same, has the same functionality. It's still being routed, but it's still 14%. And compared to the V-scored build-up, it's 31%. So this is quite a lot of money. And this can be saved by checking this, by discussing this with us. What is possible? How can we place? How can we nest our PCBs in the delivery panel and so on? And I've said it's good to know what is the usable area on our production panels. And if you use other manufacturers, just ask them what is their usable area, and then you can calculate the best array size which can be used here. For you as a hint, I've prepared this table here. I do not go into the details, but just for you to know, these gray boxes, those are the sizes which are preferably being used when it comes to assembly, because these can be handled good in assembly lines. They are not too small, not too big, and therefore these should be preferred. Please note that these gray boxes are based on the outlines of the arrays are being V-scored. So there is no routing. What you do in the array, if you V-score or if you route, that depends on you. These figures here are the outlines of the array when it's being V-scored. Some tips. The edge of an array when it's being V-scored should be at least 5 millimeter. This is due to basically your assembly line. You need some space so that the clamping or holding of the array in your assembly line takes place. When you route the outlines of your PCBs, please take in mind that there is still a routing path in this array. So the edge should be 8 to 10 millimeter because the routing path is being not calculated in this. So if you have a 2.4 millimeter routing path and an edge of 8 millimeter, you have a remaining edge of 5.6 millimeters. So please take this in note, that the routing path, if you do a routing of the PCBs, needs to be taken in account as well. When it comes to V-scoring outlines, maybe you can just use 2 edges because your assembly line has mostly 2 clamping areas, and therefore it could be possible to just use 2 edges with 5 by 10 millimeters and save space of the 2 other edges as well, so that you can place more PCBs on your array. And please take in mind that the size of the array always should be based on the thickness of the PCB, because the bigger the PCB array is, the more critical it is when it comes to bending. So the thinner it is, the more it bends, and therefore the thinner it is, the smaller the PCB array should be, so that the handling in your assembly line is still good. So let's move on to materials. And we will start here with copper. Copper is a metal which is being traded on the London or on different commodity exchanges. Here for you to give you an impression how the price develops, I took the figures from the London Commodity Exchange for copper. You can access this on different websites. And you see that there are often a lot of price steps. Here in that case, I took the figures from the last 4.5 years. And you see that from the end, or maybe October 2016, up to October 17, so within 1 year, or almost 1 year, we had an increase of approximately 50% in price of copper. And when we buy our base materials, we always get the daily copper prices. And if the copper price rises, we need to adjust our PCB price as well. Why is this important for you? Because the cost of copper is actually a big factor for the PCB itself. And I've taken 3 different substrate thicknesses here and compared the prices with different copper claddings. So I used 0.51 millimeter substrates, 1.5 millimeter and 2.4 millimeter substrates, and always had a look on 35, 70 and 105 micron copper cladding on both sides. And for 35 micron, I always took 100% as a base indicator. And you see the thinner the dielectric gets, the heavier the impact of the copper price is on the overall substrate price. For the 0.51 millimeter, this is more than 2 times 2 in a factor. So copper is quite a significant part of the PCB cost, and this is displayed here. What does it mean? The question always is, what is necessary in copper or what is possible? Do I need 35 micron on an inner layer if there is no other power going over it, or is 18 micron, 17, 18 micron as a signal layer enough? Do I need 70 micron or 105 micron due to my current in my power lane? Or could I use, instead of 70, 35 micron and make the tracks a little bit wider so that the current carrying capacity is still the same? Yes, this needs to be a trade-off. We know this. A trade-off of space during layout on the layer and a trade-off of PCB size and so on. But it just is here to give you a point where you need to think about, to not always say, oh, in the past I always used 70 micron copper, so I will still use 70 micron copper. You see 70 micron compared to 35 micron copper, for example, is quite an add-on in price for the material. Which base material should be used? Well, there is a small recommendation given by us. It's always good to talk to us, but here you can see that for low layer counts and smaller PCB thicknesses, a standard TG135 is often okay to being used if your application does not demand a higher temperature, for example. So if you only have a maximum temperature of 60 or 85 degree, the material with TG135 can be used without any issues. Normally, we say when we look on the temperature, material can be used up till 20 degrees below its TG. This is not the UL maximum operating temperature. Please note this. This is only the temperature where we say the material can be used. If you go to higher layer counts or thicker PCB thicknesses, it might be better for your wires, for example, for the reliability of the wires, if you use a higher grade material. This is due to the different CTEs of the material. CTE means a coefficient of thermal expansion. So the material does not expand that much when you switch from a TG135 to a TG150. So therefore, the overall expansion of the material is lower, and the vias are not stressed that much when you look on mechanical stress. But, as always, there is a but. Higher grade material costs a little bit more, and again, I did a price comparison. I took a 1.6 millimeter 6-layer multi-layer, used our standard build-up, and just changed the material from a TG135 to a TG150. And you had a price increase by 23%. And as you see in this chart, 1.6 millimeter, this is the point where we might start to discuss if either a TG135 or a TG150 might be used. So come to us, talk to your sales partner, talk to us, which material is best for your application, because this is the point where money could be saved. When we have the choice of materials, we will have a look on the stack up of your boards. And here we have a comparison of a 4-layer multilayer with different thicknesses. And to make it a little bit more interesting, I have a poll for you. I would like to ask you a question, and the question is, in your opinion, what is the optimum PCB thickness for a 4-layer multilayer when it comes to cost? And you have several choices: 0.5 millimeter, 0.8 millimeter, 1 millimeter, 1.6 millimeter, and 2.4 millimeter. So you change nothing in your layout. It's just the thickness of this 4-layer multilayer, which would be the best thickness when it comes to price. Please vote. So it's 40% of participants have voted, 50, 60%. So we will wait another 5 seconds. And we close the poll. So let's have a look on the results. Whoa. Almost, yeah, all of you have voted for 1.6 millimeter, followed by 1 millimeter. That's interesting. And now we switch back to the presentation and we will have a look on it. And we start with your preferred build-up. And I assume that this will be the preferred build-up because this 1.6 millimeter basically is the industry standard. Here you see our standard build-up for a 1.6 millimeter board. We use an 0.7 millimeter core with 4 prepregs, and the glass style would be 7628. When we go to very thick build-up, the 3.2 millimeter, we use basically the same stack-up, but we just change the core from an 0.7 to 2.4 millimeter thick core. The prepregs will stay the same. When we build it thinner, we change both the core and the prepregs. So we go to 2116 prepregs and an 0.4 millimeter. And when we go very thin, an 0.5 millimeter build-up, we have to change the core to 0.1 millimeter and have to change the prepregs to 1080 prepregs. So this is all standard build-ups, no special rules placed in behind. And I took the 1.6 millimeter thick build-up as 100% cost. And now have a look. And surprise, surprise, you see that the 1.0 millimeter thick build-up costs less than the 1.6 millimeter build-up. For sure, the 3.2 millimeter build-up costs quite a lot more. This is just because of the material or much more material being used here. All the processes are the same. Handling basically is the same. It's just the material price acting here. And you see we have an increase of 37%. When we go down to 0.5 millimeter, you see that the price rises again. Why this? That's basically because of 2 issues here. We have to work with an 0.1 millimeter core, and I said we have to. This means we have an increased handling here. 0.1 millimeter is basically flexible. So the handling is quite different compared to 0.4 or 0.7 millimeter cores. Those cores are rigid. The 0.1 millimeter core, even if it's FR4, but it's so thin that it's flexible. So we have a handling factor here, which comes into the price calculation. And this gives you the fact that this board is much more expensive, or is 7% more expensive than the 1.6 millimeter board, even if we use less material. The prepregs basically cost almost the same, so it doesn't matter if it's in 1080 or 2116 or 7628. This is for one sheet only a few cents difference, so this is not that much cost. This only makes an issue if we would take the 1.6 millimeter board and would replace the prepregs 7628 by, for example, 1080 prepregs. There you would need much more prepregs, to overcome the same distance between layers. So it's always the question, which prepregs do you use to overcome which distance? Okay, to sum it up, the optimum here would be to use a 1 millimeter board. There are further standards out there, 0.8 millimeter, 2 millimeter, 2.4 millimeter. For the bigger sizes, the cost would rise as well, depending on the material price. The 0.8 millimeter basically has almost the same price factor as the 1.0 millimeter. So here the prices for the cores and the prepregs do not differ that much. The result from this charts and from these figures is, come to us, talk to us, which would be the best stack up for your application to save cost again. Next would be the comparison of a 6-layer multi-layer. Again, we chose the 1.6 millimeter standard buildup. Our standard buildup is being built up with 0.36 millimeter cores and 6 prepregs. So there are 2 prepregs between each layer where we need it. So between top and layer 2, between layer 3 and layer 4, and between layer 5 and the bottom layer. Now we will have a look on the individual stack up. So you come to us and tell us, I need to have a 100 micron core in between layer 2 and 3. And to make it symmetrical, we would need this between layer 4 and layer 5 as well. What does it mean when it comes to cost? Well, again, I took the 1.6 millimeter as 100% cost. We have an increase of 16% by just exchanging the core material. Why that? I already said we have a higher handling cost due to the thin laminate, the 100 micron laminate. It's flexible, not rigid anymore. Plus, we need more prepregs in the stack up. In that case here, we have 4 more prepregs in the stack up because we need to overcome the distances between the thinner cores. So 16% by just changing the material. This is quite a lot. The next point I want to have a look at is very special build-up. For example, if you would come to us and would say, I need to have a core-based stack-up. This sometimes happens, for example, if you want to have very precise thicknesses between top and bottom layer. For hybrid build-ups with high-frequency material, this is sometimes being used, for example, when you have a Rogers material between top and layer 2, for example. But what happens if this would be done on a standard FR4 build-up? For you to know, we need to change the process completely. Although the stack-up itself looks quite the same, we tried to, here in this example, to maintain the distances from the standard stack-up to the core-based stack-up. So if you would do a micro-sectioning, it's really hard to see whether one or the other build-up is being used. You just see this by looking at the treatment of the coppers. So the treatment always points to the core side. So therefore, in the microsection, you can see what kind of build-up has been used here. But when you look on the materials themselves, it's still 6 prepregs, but you have 1 more core in the whole build-up. And when you look on the price indicator, you see that there is a rise, an increase of 22% in price. And for you to know where these 22% come from, this is due to the fact that if we have a core-based stack-up, we need to do multiple exposures of the outer layer cores. So that during our process, this 6-layer multi-layer basically has the same process flow as an 8-layer multi-layer. Why that? Well, after pressing, when we do the pressing, we need to have a fully covering copper on the outer layers so that we can do the drilling and can do the plating. We cannot use the outer layer cores and place the top and inner layer layout already on this panel. We have to secure the copper layer on top, and we have to secure the copper layer on the bottom for the bottom core. So we do a twice exposure of these top and bottom layer. First, we secure it completely. Then we do the drilling, plating, and so on. And then we do the final exposure and structuring of the outer layers. So it's comparable to an 8-layer process. And this additional price needs to be paid. And this, in that case, is 22% for this stack-up. And based on my calculation. What further costs could happen in the stack-up? Yeah, if you would use filling cores. What are filling cores? filling cores are being used when the distance between two layers is just too high to overcome it or to use only prepregs. There is a rule for us and for most of the PCB manufacturers that you have just a specific amount of prepregs which can be placed in between two copper layers. Otherwise, the build-up, we call it swims during pressing. Swimming means the registration between one and another layer cannot be handled very good anymore. So you need to have a stabilizing core, and this stabilizing core would be this filling core. And since we are not able to, or since we are not buying FR4 cores without copper cladding, we are using FR4 cores with copper, etch away the copper completely and place them into the Stackup. So if you have, like on the left side, a 6-layer build-up with 2 cores in between layer 3 and layer 4, there would be a filling core due to the distance. This again is almost comparable to an 8-layer process because we need to handle this core, this additional core. We have 3 cores then. We need to etch away the coppers. You still pay for the copper, even if we have to etch it away. You do not see it in your build-up, but this creates cost. So again, just another hint, come to us, talk to us if we can avoid this by creating an intelligent Stackup. After the lamination, we normally need to do the drilling to realize the wires. So let's have a look on the drilling process. And here we will have a look in that example on 3 different drill tools: 0.55 millimeter, 0.35 millimeter, and 0.25 millimeter. First, we will have a look on the tool life and on the panel stacking. What does panel stacking mean? Depending on the registration, on the tolerances, and on the drill tool, we are able to stack our manufacturing panels during drilling. And for example, for the 0.55 millimeter drill tool, this means we can stack up, in that case, for 1.6 millimeter, 3 manufacturing panels on top of each other and can make 3 wires with 1 drilling process if we have 1 hit. If the tool diameter gets less, the stacking is being less. And for example, for this 0.25 millimeter drill tool, we can just place 1 manufacturing panel onto the table of the drilling machine compared to 3 panels for the 0.55 millimeter. Additionally, the tool life is reduced the smaller the drill bit gets. Here you can see that this is almost half the strokes or hits when it comes to the 0.25 millimeter tool. So let's have a look on the time if we want to drill 15,000 wires. So this takes us 0.2 hours for the 0.5 millimeter drill bit. It takes us 0.4 hours for the 0.35 millimeter bit, and it takes us almost an hour for the 0.25 millimeter bit. Where does this come from? Well, it's a combination between count of strokes, how often do we need to change the drill tool, and how many panels can we stack on top of each other. We need to use quite a lot of drill bits if we have less strokes. So for 15,000 wires, this would be 30 drill bits, which we need to realize those 15,000 wires, compared to only 4 drill bits when we have a look on the 0.5 millimeter drill tool diameter. Now let's have a look on the cost, and please note that this is just the cost for the drilling process, not the overall cost for the PCB. This is just the cost in the drilling process. So again, if we take 100% for the 0.55 millimeter, we almost double the cost. When we decrease the size of the diameter, and when it comes to 0.25 millimeter drill bits, we almost increase it by a factor of 5. This is only the cost for the drilling, but this is a significant part for the overall PCB cost. And for you, to give you an imagination, what these drill tools really look like, we place them onto a 5x5 millimeter checkered paper, and you see this 0.25 millimeter drill bit. Yeah, this is the size of the lines here on this checkered paper. And if you took this drill bit and have a look on it in reality, it's the tip of the drill tool is, you hardly can see it with your own eyes. So it's always a trade-off in cost. Which drill tool size do you use? Yeah, we know that often for a layout, especially when it comes to HDI, when you use dog bone structures and so on, you might want to use those very small drill bits. But especially when it comes to HDI and structures and BGAs and very small pitches in BGAs, there is often the point where it comes to the fact that it might be better to have a look on changing some wires to laser drillings. Because as you have already seen, such drill tools, they have a specific cost, they have a specific drill life, plus what I didn't show you, they have a specific drill frequency, so how many hits per second can be done. And this drills per second sum up in the overall process cost, because the less drill frequency we have, the longer those panels are being placed on the table of the machine. This basically is cost. I just talked in the morning to a customer where we had this discussion a few months ago, and I advised him to change his build-up to an HDI build-up. In that case, he again had another point. He had filled and capped wires. We will come to this point later. And we advised him, due to the amount of wires and due to the process of filled and capped he wanted to use, we told him to change his layout to an HDI microwire build-up. And the result was that he could reduce the PCB cost by 20% by using an HDI. So this myth that HDI boards are always more expensive, well, nowadays is not accurate and true anymore. There are a lot of boards in our manufacturing where we could say, please change the layout to an HDI build-up, and you would save cost. So this is just a point which, again, you need to think about. If for some of your boards this might be interesting to change the build-up to an HDI, this really could save money. I do not say that all of your boards need to be changed to HDI, but some of them could be interesting to have a look at when it comes to very thin, small wires and thousands of wires on the board. So now we've already started to talk about microwires, and since several decades, this technology is out there already, and there is always still the discussion about voids when it comes to BGAs. Yes, we know that voids might occur when it comes to standard microwires, but please note that there is even a rule. So when you have, for example, look on an X-ray image, even a class 3 build-up allows 22% of the image diameter of the overall BGA diameter in voids. And the formation of voids can be, there is an effect on the size of the voids when you have a look on your solder paste and the flux being used in your solder paste, if you have a look on your temperature profile in your reflow oven, and if you have a look on the time for these different temperature steps, so that you have a look on the uniform heating of your board and the through heating of the overall circuit board. We have a lot of customers, even in the automotive sector, for trucks, for cars, where this is being used in controllers for gearboxes and so on, where we have boards which already run 20 years out there in the field without any issues and still are using standard microwires. But still, there might be some applications where it is necessary to fill the microwires. So therefore, we have two different technologies. And if you're interested in this, we have several presentations and webinars dealing with the buildup of HDIs and having a closer look on the buildup of copper-filled microwires. So still, you have to decide if you want to use copper-filled microwires or not, but please take in mind, filling of those microwires still is additional cost. It doesn't matter if they are copper-filled or if they're resin-filled, like on the bottom right picture. And to give you an imagination why we have additional cost, I want to go a little bit more into the detail of the technology, how microwires are being filled with copper. Here you see the sequence of a copper filling process. And there are different molecules and different chemistries in the plating bath, which are being used for this process. So first you have a wetter or a suppressor, and it's being used that the molecules, well, they basically occupy the surface. And since they occupy the surface, they block the deposition of copper. So the plating does not take that much place on the surface. Then we have the leveler chemistry. The leveler, basically the molecules, they place themselves on the location of the highest current density and block the deposition of copper there. And this is mostly on edges, for example. And then we have the brightener. The brightener basically is being used to reduce the size of the copper crystals to make this copper, which is being plated here, more reliable. Why is it interesting? Well, if we occupy the surface and if we block the edges, the copper builds up from the bottom to the top in the microwire. And here you see this in those 4 different steps. What does it mean when it comes to time? And here you see a publication from KAIST from 2019, where this was looked on it a little bit closer. You see that it takes more than 1 hour to plate such a microwire. Compared to a standard plating process, this is a factor in time of 2 to 3, depending on the thicknesses, compared to just a standard plating bath. And this factor, this is again a cost factor, so it takes more time during plating, and therefore the PCB is more expensive if you use copper-filled microwires. Another factor when it comes to HDI is the actual stack-up. So here I give you an example of 8-layer HDI boards with different configurations. And to start with the cost, again, I took a simple microwire built-up, a 161, which means it's a 6-layer multilayer. Plus you have 1 microwire layer from top and bottom, and I take this as 100% cost now. To realize this build-up, it's just like a standard multilayer. You have 1 single lamination step. If you want to add more microwires, for example, if you want to add microwires which go from layer 1 to layer 3 in one process, you need to do sequential laminations. So we have 2 pressing steps here. Or if you have inner layer microwires, then we need to do 2 sequential laminations. Maybe you might want to add buried wires, which in that case go from layer 2 to layer 7. Then you still need to do 2 sequential laminations. You can add another set of microwires, and the most complex build-up here, which can be used, would be to use even a buried wire going from layer 3 to layer 6, still use 2 microwires. And in that case, I didn't even have a look on copper-filled microwires. I just used staggered microwires so that we can use a standard plating process. And when we have a look on the cost, you see, I do not go into all of those figures, but you see when we have to do 3 sequential laminations plus 2 microwire processes plus a buried wire, this increases the cost for the PCB by 75%. So it's almost doubled in price just by a different stack-up. It's still an 8-layer board, but you have different configurations in wires. So what's the effect? What's for you to learn? Please have a look on the configuration of your board. Which wires do you really need? It's not advisable to use all the different wires being possible in the build-up. So just use the wire types which you really need. Next point is, if the PCB is basically almost finished, we need to create the outline. We do this either by routing and V-scoring. In that case, I want to give you an expression and an example about the cost for routing. And basically, it's the same as for the drilling. In the mechanical departments, we have for the routing as well the possibility to stack those panels when it comes to effectiveness of the process. But again, for different routing tools, we have different stacking possibilities. A 2.0 millimeter routing tool can be used in a 3-up stack, whereas a 1 millimeter routing tool just can use 1 production panel on the table of the routing machine. And it's the same for the tool life. The thicker the routing tool is, the longer the distance we can route with it. So we have, as an example, 15 meters for the 2 millimeter routing tool in our fabs. We have 5 meters for 1.5 millimeter routing tools, and we have 3 meters for the 1.0 millimeter routing tool. And when you sum this up and have a look on, for example, the manufacturing of 100 PCBs with 0.5 meter routing paths surrounding the PCB, this means that we have to use 16 times more tools for 1.0 millimeter compared to 2 millimeter routing tools. And this is cost which is being paid by you if you want to have those small routing tools. The feed is different, so how fast can we route through the material? It's significantly different. And this combination, so the stacking, different tool lives, and different feed of the routing tools creates different times for the manufacturing. Here in that case, again, as an example, what time does it take to manufacture or to produce 100 PCBs with an 0.5 millimeter routing path? If we can do the stacking, if we have thick diameters, it's rather easy. It's 0.2 hours, so it's rather quick. The time increases the smaller the drill, or the smaller the routing tool gets. And now again, we have another poll for you. I want to ask you another question. What do you think? What is the extra charge based on the price indication between a 1.0 millimeter routing tool compared to 2.0 millimeter routing tool? Again, I give you the times. It's 0.2 hours for the 2 millimeter, it's 0.6 hours for the 1.5 millimeter, and it's 2.8 hours for the 1 millimeter routing tool. So please decide and vote what is the additional cost when you change from 2 millimeter to 1 millimeter. Please make your vote. So it's 30%, 40%, 50% took part, 60%. We will wait another 5 seconds. Okay, we close the poll and have a look on your opinion. So let's see the results. And the results say you think it's an increase of 300%, followed by 800%, and it's only 4% guessing the factor 12. Okay, let's have a look onto the presentation and let's go into the real figures. So again, I took the 2 millimeter as 100%, and you already see when we change to 1.5 millimeter tool, we increase the cost. It's only for the routing process, so not for the overall PCB. We increase the cost by factor almost of 3. When we go down to 1.0 millimeter tool, it's a factor of 12. Why this? Well, it's because of the combination. We cannot stack panels. We have less tool life, and the feed is a quarter of the feed of the 2.0 millimeter tool. So we have a long time on the machine, and therefore the routing cost is much, much higher. What does it mean for you? This is important when it comes to routing of your outlines. If you have a standard outline, there is no issue using big routing tools, 2 millimeter, 2.4 millimeter. But on the right side, you see a board. Well, here you have cutouts which need to be done. And it's interesting for you to know that those cutouts, even if this is just a 2 millimeter wide cutout, we cannot use a 2 millimeter tool. We need to run along the outline, which means we go into one direction and then on the other direction, because we always touch one part of the outline with the tool. So if there is a 20 millimeter long slot, it means we have a routing path of 40 millimeter, roughly spoken. And then it's again a factor for the routing tool itself. The smaller this slot gets, the more critical it will be for the routing tool. And I already said the feed is less, but the stability of the tool is less as well, which means if we go below routing tool sizes of 1.6 millimeter, we need to have an overlap of 80% in material so that the routing tool doesn't break. So this means if you have a 1.6 millimeter slot, for example, we would need to use a 1.2 millimeter tool or 1.4 millimeter tool so that you still have enough material there. I think it's a 1.2 millimeter tool, sorry about that. So that there is still enough FO4 material remaining for the drill tool to drill through it. Otherwise, if there is too less remaining material, the routing tool is being bent to the side and it might break. The wider or the thicker the slot, and the wider the slot, the thicker the routing tool, this effect is not so critical anymore. So with a 2 millimeter or 2.4 millimeter tool, this is not that big of an issue, but still you have the doubled path because we run along only one part of the edge. And on the right side, you see that therefore the routing path is much, much longer than just on the left side. And therefore this takes more time on the routing machine, and therefore it increases cost. So therefore it's for you to take with you, have a look. Do you need those additional slots, these additional routings in your outline or not? If so, please have a look on it regarding tool sizes which can be used. And please have a look, for example, on inside corners, on the radius of the inside corner. How big can this radius be so that we can use a bigger tool? Maybe it would be advisable to have a cut back into the board to use a bigger routing tool to use different radiuses. Okay, let's move on to different other technologies. What else could increase your cost? We've already spoken about a lot of layer counts and PCB thicknesses. This is not only relevant for drilling and routing. The more layers you have, the more effort we have in inner layer structuring, the more cost is being created during stack up because it takes more time to stack up the whole built up and so on and so on. So more layers and thicker PCBs mostly increase the cost. The number of laminations, I've already talked about that one in a little, but if you need sequential build-ups, 2 laminations, 3, 4, 5 laminations could be possible. This increases cost because you always have to run through the pressing department. It always takes several hours to press such a build-up, and this is being summed up in the overall cost. Then we have the so-called edge plating, or depending where you come from, it's often called side plating. So edge plating or side plating, you can see this here, means that there is copper being deposited on the outline of the board or on parts of the outline of the board. And this copper deposition needs to take place during the same phase and during the same process in plating for the wires. So we have to split the routing process. We need to do the routing for this edge plating before we go to the plating process. So we need to go 2 times or 3 times, depends on how the outline is being created, to our routing process, and this adds cost as well. It's the same for castellated holes or castellations. Here as well, we have to divide the routing process. We have to have additional processes to create these half-opened wires on the edge of the PCB. Then we have to have a look on colored solder resist. There are different solder resists out there. Green is basically the industry standard, but there are white solder resists, black, red, blue. And yes, we know that there are some applications out there which really require, for example, white or black solder resist in LED applications, for example. But still the problem is, well, the demand for this kind of boards is extremely low, so that for a PCB shop, it's not affordable or not being doable to have several machines for each solder mask. So the solder mask is being put onto the manufacturing boards by using the same machine. And this means if we have green on the machine, we have to clean the machine. We have to remove the green solder mask everywhere. We have to place the other solder mask into the machine. We have to do a check in printing. Then we can run the process with the different solder mask. And if we want to do green again, this means taking the other solder mask from the machine, cleaning it thoroughly, setting up the new solder mask, for example, green again, back to green, do the testings if everything in the process works correctly. So this creates quite an effort in manufacturing, and therefore this is being placed onto the cost of your panel if we change the solder resist from green to any other color. We know sometimes that customers use, for example, a red solder resist or just another solder resist other than green to mark their PCBs when it comes to prototypes and samples, so that they are not being used for series production. Here it might be interesting to think about using color legend printing, for example, printing red or yellow onto these boards. This can be even done in big arrays, or even almost the overall board can be covered with legend printing, so that this board basically has another color, and you still can decide if this is a board being done in a prototype process or in a series process. Legend printing, I already talked about this one here, that you can use legend printing, and if you already use legend printing, this version is not that much of a cost increase. And for the legend printing, please take note that, yeah, the question always is, how small must it be? Your CAD tool, doesn't matter if you use Altium or Cadence or whatever, Zuken, well, on the screen, you can make very small writings. But is this being done on the PCB board as well? So here there are limitations. So on the one hand side, if you can read it or if it's machine readable, on the other side, if it can be printed at all. The danger always is, due to the different tolerances we have in a legend printing compared to a solder resist printing, is it might happen that the legend printing, if it's too close to the pad, that we print onto the pads and therefore might create an issue with the solder process. So have a look on your legend printing. How small must it be? Which tolerances do you need? How far is it away from solder pads? Next technology we want to have a look at is impedances. And you need to know that there are different steps of impedance manufactured boards. One step could be, and depending on where you come from, this is called impedance watching or controlled dielectric build-ups. For impedance watching and controlled dielectric build-ups, we have a very close look on a stack-up. We calculate the stack-up regarding to your needs. We have a look on the track widths, but we do not place any kind of TDR coupons on it. So we manufacture the board based on our experience and based on the IPC rules and tolerances, and send out the boards in that way. If we want to control it, control means we need to place coupons onto a manufacturing panel, and on the right side you see those kind of coupons, and they take a significant part of the production panel. So you cannot place that much PCBs on the manufacturing panel because you have to place those coupons on the panel as well. So when you look on cost, it means less PCBs. We've already talked about the occupancy. Less PCBs, the cost is being increased because you have less PCB. Plus, we need to test those coupons. So there is cost being created by testing those coupons. And these coupons need to be tested for each lot. So this is not a single cost, an initial cost, it's an ongoing cost, and this has to be paid as well. So it's the question, do you need controlled impedance or is controlled dielectric enough? For us, in our experience, we know our processes very well, we know our manufacturing very well, and therefore basically 85 to 90% of the boards in our house which have impedances, they are just being controlled dielectric build-ups. And we see that there is no increased yield or decreased yield if we have impedance control boards, if we control those coupons. So we do not scrap more PCBs just because there are coupons on it. It's just that you have a piece of paper where we confirm that the boards really have this impedance. Next point, and I've already mentioned this during an earlier point in this presentation, wires filled with resin and plated with copper, the so-called filled and capped wire type 7. The question always is, do you need this kind of build-up? We know that there are a lot of applications for this. Examples are cooling areas, so that you place wires in big ground areas so that the components are being cooled down and the heat is being transferred to the backside of a board. If you have wires in solder pads, you would use this so that the solder doesn't flow into the hole. Or if you need vacuum-tight PCB so that no air exchange can be from front to backside. But the question always is it necessary or can it be avoided with intelligent design? For example, to switch over to microwire technology. There you do not have a through hole, so the solder doesn't flow away. Or on the bottom right side, you see an example where the wires have been removed from the pads and even have been removed from the ground area to the edge of the ground area, so that still you can do the plating. You have a specific amount of heat which can be transferred to the backside, and still you do not need to fill the wires with resin and overplate them with copper. So it's always the question, which technology do you use? And even by changing from filled and capped to HDI build-up, I already told you that depending on your layout and depending on how many wires you really have, this might even benefit the board, or you might benefit from less cost. Next point I want to talk about is you're requesting us to produce the PCB according to IPC class 3. Often we see that this requirement of manufacturing according to IPC class 3 is mistaken with the requirement of having, or the need of, 25 micron copper in the barrel. Why do you use thicker copper in the barrel? Basically, this is again a reliability issue. The more copper you have in the barrel, the more reliable is this copper barrel. But yes, we know that this is the intent of IPC class 3 as well. But IPC class 3 is not only putting 25 micron copper in the barrel. There we have to look, for example, on remaining rings, on the wires, on the pads, and there are basically 14 significant parameters which need to be looked on when we have IPC class 3 compared to IPC class 2. And those 25 micron copper is only one part of IPC class 3. So we have stricter criteria and we need to test this. We need to clarify if we really meet IPC class 3. So we have an additional testing. We have therefore often a lower yield because of these more critical tests and critical parameters, and therefore the price increases quite a lot. And to give you a figure, this might often be between 20 and 30% increase of price by just placing IPC class 3 in your request compared to IPC class 2. If it's only for the 25 micron copper, then please come to us, talk to us, and place this 25 micron copper in your PCB specs and remove the IPC class 3 requirement. This saves quite a lot of cost. For sure, if you need IPC class 3 boards with all the other parameters, then yeah, use IPC class 3, we can do this. But as I said, we see that this is often a mistaken requirement by 25 micron copper in the barrel. Next point would be electroplated gold. The usage, for example, is contacts as an abrasion resistant surface. And it's often being used selectively in combination with nickel gold. And it can be plated up to thicknesses of 4 millimeter in our fab. And for you to know, we calculate the daily price of the gold. So the more gold you need, the more cost is being created. And this can be factor 5 or even more, because this depends on the daily price. And again, I took the London Commodity Exchange here. And if you have a look on the differences, the last 10 years, you see that nowadays, today, due to all different factors, especially Corona crisis, we have a quite high gold price at the moment. So it's always advisable to come to talk to us, which would be, if you need electroplated copper, which would be the required thickness, the best thickness, and not just tell us use 4 micrometer, because maybe 2 micrometer would be okay, and the cost is much less. When we talk about different technologies, we have to look on flex rigid stackups as well. Here in that case, we compare a 6-layer build-up, and the difference is we have 1 layer going over the flexible area compared to 2 layers going over the flexible area. In the left side, the flexible area is, or the flexible layer is on the outside, and on the right side, the flexible area is in the middle of the board. What does this mean when it comes to cost? Well, to realize this flexible area on the right side, we need to go 2 times onto the routing machine. The routing always takes place from the top. So we have to do the routing from the top, and on the right side, we need to turn the manufacturing panel so that we can route from the bottom as well, because then the bottom is turned up. On the left side, we have just this one depth milling process. Then we have a difference in material price, because on the left side, we only have 1 copper layer on the flex material, whereas on the right side, we have 2 copper layers on the flex material, and therefore the flex material is much more costly on the right side. Then we can use, for this 1 flexible layer, we can use a screen printed flexible solder resist, whereas on the right side, we need to route and laminate polyimide coverlays on the inner layer, flexible layer. And to increase the reliability even more on the right side, we often need to use a partial covering coverlay. This is often being called the bikini coverlay. And this is a handmade process. So there is no machine out there on the market where we can place this coverlay pieces onto this board. This needs to be done by hand. They need to be fixed by hand. So this quite adds a significant factor in cost. And you see this can often be almost a factor of 2 in cost for these different build-ups. So let's come to the end, just for a few more slides. For us, when it comes to error prevention, what we see quite a lot is that, for example, a build-up or a layout like this one here, and if the rules in your CAD tool are not set properly, when it comes to clearances in the same nets, something like this here indicated can happen. The track runs too close to the pad, the clearance is too less, and our design rule check is going to give us a note. And then we have to talk to you and say, please change this because this is not producible. On the bottom right side, you see a rectangular track going into the pad. This is not an issue. So please have a look on your design rules that even clearance in the same net is being looked at so that the left side error is not being done. Because either this place takes cost in our initial processes when we do the design rule check, or if we do not find it, this still might make issues when it comes to AUI checking. This produces pseudo errors. These pseudo errors need to be checked, and this check, produces cost as well. Another point always is looking at clearances to outlines of copper planes, copper lines, and holes. So due to different tolerances and due to different manufacturing issues, we need to have, depending on the technology and depending on the stack-ups, 200, 250 or 300 microns. You will find this in our design rules for the clearance copper to the outline. In that case, we have 150 microns. This would lead to our design rule checking department getting in contact with you and telling you, please change your layout because this cannot be produced. And this does not create cost in the PCB manufacturing itself, but still it creates cost in your house, and this cost can be avoided. And there is always the question, please have a look into your layout. The more effort you place in your rules, the more effort you place into your layout, even if it takes a little bit more cost in your house, it still might save you a lot of cost when it comes to series production, because each PCB could cost less, so that the increased cost in your house easily can be matched by the decreased cost in our manufacturing. Last point, this is just a small hint. When we look on a data format, still 90 to 95% of our customers are using the Gerber format. But what we often see still is that the preset parameters in the CAD tools are 2.3 inches in the Gerber data. But when you have a closer look, what does it mean is you have a minimum resolution of 25 microns, which is If you work with 100 micron track and space, yeah, quite an issue. So it would always be better to go to 2.5 inches or 4.4 metric parameters, because the resolution is much less. What is the issue here? When we get your data, we need to put it into our system, and so there are some different conversions in data going on, and the higher the resolution, the more it can happen, especially when you mix the parameters. For example, your drill data is in inches and your layout data is in metric parameters. Our tool needs to convert this. And when you look on the tolerance chains, there could be the issue that, for example, when you look on the drilling, the middle point of the drill and the middle point of the pad do not fit anymore due to these different conversions and due to these different resolutions. And therefore, this creates effort in our design rule and input department, because then those middle points need to be matched again, or we send back the layout to you and tell you, please use a different parameter set so that these middle points are being matched. So this saves cost again, because work doesn't have to be done. So to sum everything up, and I do not want to go into the details of this chart, I just want to give you the impression that there are a lot of points you need to look at when it comes to cost of the PCB. It comes to design and the complexity of the design, materials we have talked about, processes we have talked about, sequential build-ups, via filling. We have talked about the sizes of the board, volumes for sure. The more boards we manufacture, the less cost often is being created. So if you only have one board, yeah, this costs quite more than 10,000 boards. And then there are some additional costs you have to look at. For example, packaging. Do we need to place the boards, for example, into moisture barrier bags? This costs more than our standard packaging. What kind of tests, qualifications do we need to do? Do we have, for example, PPAP? Do we need to have UL registration? A standard UL process costs us several thousand euros. So this cost needs to be taken in consideration as well. And all these kind of stuff and points need to be think about and looked at when it comes to cost in the PCB. So this was the last slide. I would like to thank you that you stayed this long time with us. Thank you very much for your attention. If you have further questions, please do not hesitate to contact us and we will try to answer them. And for this, I will hand over to my colleague, to Andreas, and we will start with the question and answer session. Thank you very much.